this was the last pH calculation of a buffer that we did together. Here's a solution. The best way and easiest way to calculate the pH of a buffer is by using the Henderson-Hasselbalch equation. You have access to the Kas, probably even the pKas, and the rest is straightforward, so you don't really need those ice tables, but it's up to you. Whichever way you want to get to the solution, you can. All you have to recognize what the acid equilibrium is and where to get the pKa. I suggest that you try this. It is a little bit different because here we have a mixture and I'm giving you the molarity of the mixture, so the volume is irrelevant. The conjugate base over acid ratio is the same, but here I kind of prepare a buffer. I give you a volume, a concentration of the acid. This is a different acid, of course, so you'll also have to find out what the pKa for it is, and I mix it with a volume of a source of a conjugate base. So this goes back to chapter 8 and how to get from volume and molarity to the number of moles and then back to concentrations, initial concentrations, right? And that's what we're after here. So M1V1 equals M2 V2 might come in handy. Okay, so you might have noticed that there's a relationship between the way we calculated the Ka using the ice table, not the Ka, the pH, of course, the hydronium ion concentration and the negative log, and the way we set up the Henderson-Hasselbalch equation, right? So we have this relationship here. Of course, the Ka equals concentrations of products over reactants, and if you solve for the concentration of hydronium, you end up with this expression, which is the Ka times the conjugate acid over base concentration. If you take the negative log of both sides, you end up with the Henderson-Hasselbalch equation. Not all that important, just thought I'd throw this at you. Okay, let's do one more. Use the Henderson-Hasselbalch equation. That'll be the easiest. So here we have a benzoic acid. I'm telling you what it is, so you can look up the Ka or the pKa, or you can just take that number here, take the negative log, and so the pKa equals 4.19, and so if I do the pH equals to 4.19 plus the log over the ratio of base over acid. The source of the base here is the sodium benzoate, which is 0.150, and here we have a premixed mixture, so we don't have to worry about volumes. We're not given any volumes, and then the concentration of the acid is 0.050, and if we calculate that, we get 4.66. Little side note here, if the ratio of base over acid is larger, right, like here, larger than 1, then you get a pH increase. You know, it's become the base is more concentrated than the acid, you're going to have an increase in pH. If this is the opposite, if the ratio of base over acid is smaller than 1, you have a decrease in pH, and so the pH would go down. This is the problem all worked out. I used this equation here. I didn't bother with the ice table, but you can. But you should always look at do the test, because if the test doesn't work, then the Henderson-Hasselbalch equation also doesn't work. So do your test, make sure that you have a dissociation that is less than 5%, just like we did for acids and bases. Here's another one for you to work on your own. I highly suggest that. Don't just work active, work some of these as well. Same idea, different acid. Okay. How exactly does a buffer work? It's a simple matter of Le Chatelier's principle. If we have an equilibrium of a weak acid, generic one is shown here, and we want to control the concentration of H+, as you add more H+ to it, this equilibrium will shift to the left, deplete the conjugate base, and form more of the acid. So this would then deplete, and you're not controlling it. But if you are increasing the amount of HA you have, you can shift this to the left a lot more, right? So if you are increasing the conjugate base, you can you won't be able to deplete that equilibrium fast. And so the same is true for bases. If you're adding a base, you're going to shift this equilibrium to the left. You are breaking this up, forming more of that. And so if you have a large amount of the weak acid as well, then you can also prevent depleting that equilibrium and increasing H+. So you are going to be reacting the acid. So another way to look at that is if you're adding a base to this, you're gonna shift this over. You're gonna have OH react with H+, forming water, and as long as you have a source of the weak acid, it can keep on shifting and replenish that amount, and it will form more conjugate base. So a good buffer will have an increased concentration of HA and A minus. So if you have large amounts of each of these, and the larger those amounts are, it's the better the buffer. Okay. So this is just a cartoon illustration of a buffer here in the center, and then what happens to each of the concentrations of the conjugate base and the acid as we add acid and base. So it makes sense that the hydroxide would deplete the acid concentration, increase the conjugate base, whereas the acid, if you add it to the system, will deplete the conjugate base concentration and increase your acid concentration. Also keep in mind, what controls the pH is, of course, this right there, and that's kind of like in the middle. That's what you're trying to control. And of course we have this relationship as well. Goes to water, right? You've got that. What you really should look at is the auto-ionization, H2O going to H3O plus and hydronium ion. And so that concentration is of course related to that and the balance here. All right, so we can have acidic buffers and basic buffers. I mentioned this already. We are familiar with the acidic buffer. You have a weak acid and a source of the conjugate base, but you can also have something like ammonium, let's say bromide, aluminum bromide, and ammonia together. If you mix a solution of ammonia and ammonium bromide, let's say a 0.5 molar solution of each, you are creating a buffer that will have a pH larger than 7. And so you can have any source of soluble bromide, right? So you can have ammonium chloride, ammonium bromide, ammonium acetate, or maybe not. Or what happens if you use ammonium acetate? Or ammonium fluoride? That could be interesting, right? Well, I'll let you think about that. So this is just, we've looked at this relationship already. I made a big deal out of it in lecture 2. But if you wanted to create a buffer, let's say with a pH of 3 or 4.0, I would start with something that already has a pKa that's close to 4, and then we'll actually do a calculation later on. But if you wanted to create any of these buffers and decide what to mix together, you want to have a source of the acid, in this case the formic acid here, and a source of the conjugate base. So we need some sort of sodium formate or potassium formate, and mix the two to get a buffer. And the same is true for a basic buffer. You can take any of these amines, which are all weak bases. Let's say pyridine here. You mix some pyridine and then a pyridinium salt, right? So this is the pyridinium, the conjugate acid of, you see all it is, it's a hydrogen added to this basic amine and formed this cationic, just like ammonia does with acid, with hydronium, H+, it forms the ammonium ion. So this is the pyridinium ion, so you use this, a chloride. Probably the best solution is a chloride. I already went through this. This is the equation that relates the acid and the base, but of course it has to be, in this case, if you have ammonium ions, the Kb for that, so H2O forms ammonia and hydroxide. So if you have, let's say, ammonium chloride, that would have this equilibrium expression here. Now it's very pretty. Would be associated with a Ka, and so that Ka can be calculated with this formula. So you take the Kw divided by the Kb. Where does the Kb come from? Well, it's the ammonia Kb. So ammonia has a Kb of 1.8 times 10 to the minus 5. You plug that in, you can calculate the pKa. This is not the pKa, the Ka for ammonium, right? And that Ka for ammonium chloride or ammonium bromide would be identical, because the counter ion is irrelevant unless the counter ion is also a conjugate base, and then you have a little bit of a problem. This is another equation that's quite useful when dealing with acids and bases.